All right, everybody. Hello. Welcome to today's DeepSeek-R1 paper reading. So I'm Mike. I'm going to be going over the paper reading here today, and let me just share my screen so we can kick this off. All right. Now, before we get started, I saw a really interesting tweet or X post, and one of the things that I wanted to cover was Mark Chen's reaction, because I think people were aware that it happened, but we didn't really talk too much about it. So I really like the fact that he's congratulating DeepSeek for producing an R1 or an O1 level reasoning model, because their research paper demonstrates that they have independently found some of the core ideas that they did on their way to O1, which to me is really a fascinating thing to say, because it kind of gives away a little bit of the game that for the most part, this is probably about as close as we're going to get to an O1 sort of release paper. I feel like, because we're probably not getting one from OpenAI at this point, especially since they're likely going to be moving on to O3. But a lot of the core ideas that leverage reinforcement learning, I think, are going to be really relevant from R1 to really understand why models like O1 are performing as well as they are. Since it seems like there are significant core ideas there that are really what kind of make R1 as good of a model as it is for what was released by the company DeepSeek. And just real quick on the corporate structure, DeepSeek is the AI company owned by Highflyer, the hedge fund, and it is the subsidiary of said Highflyer hedge fund in China, which is owned technically and operated by essentially the same people, more or less, but it's just a different corporate structure. So it's reasonable to use Highflyer and DeepSeek interchangeably, but it kind of gets a little weird when you're talking about development of the model versus actually who owns and funds it, because it turns into more of like a Microsoft to OpenAI relationship at that point. So I'm just going to refer to the company as DeepSeek moving forward through the paper, unless I have a particular reason to talk about, say, the funding, which to some extent I will cover. But anyways, let's get to the paper itself. So there are big elements of this paper and its introduction of DeepSeek-R1-Zero and DeepSeek-R1, as well as the additional distilled models with 1.5 billion, 7 billion, 8, 14, 32, and 70, all distilled from the R1 model and based on Quen and Llama for those model distillations, right? So those are kind of the core things that we're going to be talking about in this paper. Now, for understanding these models and why they're kind of a big deal, a lot of what we really have to end up looking to primarily will be the post-training, but the pre-training is also pretty relevant as well. And throughout this paper, I'm also going to be going over references to DeepSeek v3 and to DeepSeek Math, as they both kind of cover in more depth some of the topics that are in the R1 paper, as well as some of the optimizations that go into the base model that gets used for training in the post-training capacity of R1. So that reasoning training process is referenced significantly more as it relates to the policy for DeepSeek Math, and more so the little tricks that really optimize the base model itself, which is what they trained R1 on top of for DeepSeek v3. So again, I'll be making occasional references to those, but I'm going to primarily stick to the R1 paper. And really what the R1 paper benefits the most from here is this sort of inference time scaling, or this process by which you just pump in a bunch of compute to fire out a bunch of tokens as it relates to the inference or output provided by the model. So it can essentially process and essentially produce input or output tokens before providing a final answer. And that's really what inference or thinking models do, right? These inference-based test time, or I'm sorry, test time scaling models, where they're just processing and producing tokens before providing an output. And that's really what a lot of this technology is. It kind of just bakes in this sort of chain of thought reasoning process into these models themselves. Now, ultimately, the challenges related to effective test time scaling still remains a sort of open question for the research community, like how to properly optimize, what are some of the benefits, what is the real recipe that we can really leverage to get the most out of test time compute, and how this new scaling paradigm comes in relative to pre-training, given that it is more of a post-training process. So after the base model is created, we go through this sort of post-training process to get it to maybe be instruct fine-tuned so it can do question and answer. And then from there, we get to a reasoning training where we have the model essentially going through these different traces of reasoning. And we're going to explain why that doesn't necessarily need to be the clear-cut way in which these things come together. You don't necessarily need to do it like that, and they don't even necessarily initially take that sort of approach in the R1 paper, as we'll see with R1-Zero how they ultimately leverage this just straight to reinforcement learning process to train up their base model V3. But there are some drawbacks that come in depending on the base model that one needs to be aware of, and like I said, we will get to that in a bit. But we kind of see through this paper that the fact that they're using these different sort of reward models for these rule-based reward models that they covered previously in DeepSeek Math, where it's an outcome-based reward model as opposed to a process-based reward model, and how they're ultimately leveraging reinforcement learning as opposed to these different search algorithms like Monte Carlo tree search or beam search, because ultimately none of these like methods have achieved this sort of general reasoning performance that we've been seeing out of O1. And this whole R1 project is really their kind of process to try and figure out what was going into O1. And essentially they came into what they consider this pure reinforcement learning, which it's kind of debatable as to whether or not it's actually like pure reinforcement learning, just because you have to kind of tweak certain things around with the policy. You have to make certain adjustments. They go through this whole like supervised fine-tuning process for R1 itself versus R1-Zero. And we're going to, like I said, get more into that a bit later, but really a lot of it's just building on the DeepSeek V3 paper, particularly the model out of that paper, which is their base model, through their particular policy optimization called group relative process optimization, or GRPO. And that's their policy that they work to optimize. So ultimately, one of the main takeaways in order to figure out the use of reinforcement learning was trying to actually get that initially to work with the model itself, like the base model, which is what they used to achieve the performance on DeepSeek-R1-Zero, which was something that exhibited superior performance on reasoning benchmarks. They focus a lot on pass-at-1 scores for benchmarks like AME 2024, with significant increase in performance, in addition to leveraging majority voting for the score as it achieves further improvements that could reach a certain parity of performance, for lack of a better phrase, because match is not quite what I would describe it as. I would say it's comparable is probably better, or in parity or with parity of a model like O1. And I'll get into my critiques as to why I feel like that's a little bit of an exaggeration, but for the most part, all papers do that. But anyways, really the whole process started with R1-Zero, where they incorporated this small amount of cold start data. Well, actually, to get to R1, they included this cold start data. But R1, they just apply the GRPO training on the base model. And you can just do that. Like, that's one of the really interesting things to come out of this paper that I feel like a lot of people don't like really consider or really express as one of the major insights of this paper, is that you can just apply reinforcement learning at inference, and the model will just kind of teach itself how to reason, which is really neat and something that didn't seem super intuitive before this paper for a lot of people in the research community. It's not to say that there wasn't an understanding of the value of reinforcement learning per se. It's just that a lot of people were trying to drop it in favor of using different policy optimizations like direct preference optimization, or DPO, which we're starting to see being more of the standard policy being applied for post-training of models, where we're getting them to be like question answering instruct-based models, right? So this introduction of, hey, you just use reinforcement learning at inference on a base model and you can get it to reason, it was really just kind of a big insight, and something that I was surprised wasn't covered more, because you see, if you look at the downloads on Hugging Face, like you have nearly 1 million downloads for R1 itself, like the full model, but like only like 20,000 for R1-Zero, which again, for performance, I kind of understand why that's the case, but I just feel like it's R1-Zero is just generally a more interesting model, even if it isn't necessarily a more performant one. But ultimately, what really makes R1 versus R1-Zero is how it ends up incorporating a small amount of cold start data into this sort of multi-stage training pipeline, where they just take this initial data and then fine-tune the base model on it to kind of create a sort of instruction an instruction-based model where that sort of question answering already exists, and then from there performing reasoning-oriented like RL. So that same technique being applied to R1-Zero just on the base model is now just being applied to more of an instruct model. And then towards that reinforcement learning convergence, they create some additional supervised fine-tuning data and use rejection sampling for that current RL checkpoint that they've gotten to. And then finally, from there, with that supervised fine data from DeepSeek v3 in these different more non-deterministic domains, like writing, well, maybe not non-deterministic, maybe non-reasoning focused domains. They have a better word for it in the paper, but I don't remember it right off the top of my head. But basically, writing, factual Q&A, self-cognition, maybe less STEM-focused fields or areas of knowledge, less generalized sort of reasoning is probably a better word for it. But then they essentially collect that information and do a retraining on the DeepSeek v3 base model. And they go through that whole new fine-tuning process on the data with an additional RL process. And then from there, they achieve a checkpoint that they call DeepSeek-R1. And we're going to go through a bit more of the paper and really break down what that means. And that process goes into more in depth. I just wanted to give like a broader overview based on the introduction. All right. By the way, if anybody has any questions throughout the paper, feel free to raise your hand or feel free to interrupt me. So I'll be happy to answer questions where I can. I'll try and pause as well throughout the paper just to kind of give people an opportunity to do so. But yeah, just wanted to make sure everybody was aware there. Anyways, so some of the major contributions that they outline from this paper is the post-training. Oh, thank you, Aaron. This question?
The other Aaron Tellis has a question.
Oh, awesome.
In the chat, it says, has R1 been tested on ARC AGI benchmark? And I said, according to Perplexity, yes. And I think I've also read that somewhere else.
Yeah, I believe that was the case too. I don't remember what the results were, but I wouldn't be surprised if they were maybe like slightly below 01, honestly, just generally, because that's the impression I get from this paper. It's not quite at the level of 01 in terms of like completely surpassing it, as much as it is like really close and roughly comparable to 01. So again, from that benchmark, I wouldn't be surprised if it was like maybe second place to it relative to 01, with 01 just barely being ahead or maybe being somewhat more ahead. But yeah, I haven't actually looked at that benchmark specifically. Honestly, ever since 03, the 03 numbers came out, I haven't really been taking ARC too seriously, because it seems like the goal is to saturate the initial ARC benchmark and then trying to get a new one set up because that one's about to be saturated. So the current one I'm not super focused on, but we want all types of tests. I don't want to necessarily put down one test versus another. I will kind of skim through the benchmarks towards the very end here, because that's not really something I tend to focus too much on generally with these paper readings, because it's just hard numbers that don't really correlate to anything that we can really grasp to conceptually outside of what the benchmarks outline. Like, we don't really know generalization as much beyond those domains, which is more so what I care about as it relates to this. But I hope that answers your question. Aaron, is that another question?
Yes, I do, just because I know you're not talking about benchmarks in detail. I guess, like, what advice can you give for anyone that's like an independent researcher trying to think of, testing their own evals, or just in general, like the general rule of, is this reproducible, right? Can we just run one of the models like on our laptop? And is that like comparable to like what, is the actual benchmark here? Like, not everyone has like massive compute and data centers. So, what can they do to, say that they have something comparable, like, hey, I've run this benchmark, this is real, rather than just depending on like the larger corporations that have access to a ton of like H100s that can run a said benchmark.
Well, that's an excellent question, Aaron. I actually do have some information set up for the evaluations later down, but the TLDR for that, before we get into it, is going to be figure out what they use to do the benchmarks. So if it's particular like eval frameworks, like SimplyBench or Simply Eval, I should say, and like the eval one from OpenAI, which is one of the benchmarks they end up using here, essentially trying to copy that and essentially duplicate the results is usually a good way. Like, a lot of the information for evaluation, you can find a good chunk of it within papers themselves, especially if you dig far enough into the references to the original paper where they're pulling the benchmark from. And a lot of the more common benchmarks like MMLU AIM, GPQ-A, you're generally going to have already built into evaluation frameworks. Like I believe Simply Eval, I think they use that to cover those particular benchmarks, which is an open source framework made available through OpenAI, and is the one I believe that they were using for conducting the evaluations for their models. So a lot of people use that, and they use that in the R1 paper as well to do their benchmarking. But yeah, ultimately doing that, maybe like renting a GPU or set of GPUs to run the full models and then conduct the evaluations from there could be an option. It just kind of depends on, and also considering developing your own evaluations, because the community is always looking for more evaluations just generally, because we're kind of not really sure how we can continue to test these models. Like there are a few things that I'm going to mention that I think are important that I think a lot of the community doesn't focus on. But beyond that, like having more difficult, like pass at one type evaluations never hurts, and is something that the community appreciates, just as it relates to figuring out the frontier capabilities of these models. So I hope that answers your question for right now. And like I said, I'll go into a little bit more of that later in the paper.
Yes, sounds good. Thanks.
Right. So with that being said, yeah, like I said, post-training, large-scale reinforcement learning on the base model. So DeepSeek-R1-Zero demonstrates that initial capability through self-verification, reflection, and just generating of long, chain of thoughts or COTs. And really, this is kind of the first research paper, like the first open research paper to validate that reasoning capabilities of LLMs can be incentivized purely through RL. And I kind of highlight and emphasize that capabilities of LLMs can be incentivized. And I'm going to go into a bit more depth of why I think that's the case a bit later. But I think it's important to pay attention to that phrasing in this context, because ultimately, it speaks more to why reinforcement learning is working so far with LLMs and where it's likely going to go. And like I said, I'll get into that just a smidge later. But ultimately, this pipeline will benefit the industry by creating better models. And how it creates better models is really kind of the big question that you want to consider as we continue through this paper. So we also see distillation of smaller models becoming more powerful through leveraging these larger models or better reasoning models. Ultimately, we still have the qualitative results of DeepSeek-R1 distill at the 7 billion parameters achieves 55.5% on AME 2024, which surpasses the larger 32 billion QWQ preview model. And we have the R1 distill of Qwen32 scoring 72% on AME 2024, 94.3%. Now, the AME 2024 evaluation, just so we go through that just real quick as an example, are different problems and solutions that I believe are math-based, if I'm not forgetting that correctly. Let's double check. Yeah, these are just math problems essentially, and there are other math-based benchmarks, but a lot of the benchmarks they tend to focus are on more deterministic tasks like mathematics, as well as coding. I believe coding challenges through like code forces. They mentioned some more information about that. And those are really the big things you want to pay attention to with these more reasoning models, just generally because these are the more deterministic, like right, wrong answers they tend to train on, and that's what they want you to focus on. So you do want to keep those things in mind as to what we want to think about what these models are particularly good at, things like mathematics, more STEM-related tasks, such as like coding, things along those lines. In addition to general reasoning, which are usually the three main types of benchmarks you see related to these types of reasoning models, right? So ultimately, we just get overall better scores on these different sets of tasks in relation to these even these distilled models, not even the full R1 necessarily. But overall, with reasoning tasks, we get higher pass at 1. On evaluations like AME, on Math 500, we get 97.3. So again, getting really close to saturating the AME 2024 benchmark and essentially saturating a Math 500. Now, for quick clarification to anybody who isn't familiar, when one says saturating a benchmark, because I know I've been saying that a lot, what it means is that you're essentially taking this benchmark and you're achieving near perfect performance, because you're probably not going to get 100% performance on a lot of them, just because some of them are not particularly well put together. Like they have certain unsolvable, unanswerable questions. So usually if you're like 95% plus, most people would generally consider a benchmark to be solved at that point. Especially if you're talking about like beyond human performance on that given benchmark in a lot of cases. Usually human performance-based benchmarks usually only cap out around like 70 to 80 something percent, where human beings are generally like able to do that but not too much more beyond it, unless they're like experts in their given field. Yes, Philip. Mike's muted. I can't hear you. Well, it's not muted, but your audio's not coming through. No, sorry, can't hear you.
Philip, you want to put your question in the chat if you have issues with your mic?
Yeah, I would appreciate that. And Aaron, if you could read that out, I would appreciate that as well. All right, thank you. But yeah, so ultimately we have these benchmarks on different things like reasoning tasks, mathematics, coding, general knowledge, stuff along those lines. So ultimately, again, we're getting near saturation for a lot of these different benchmarks as it relates to these types of reasoning models, which is something really interesting to essentially come out of these sorts of reasoning models that are now starting to kind of take the world by storm, right?
Sorry, what is the pass at one? What does that mean?
We will get to that. They actually do a full explanation later in the paper. And that is a great question. I would love to talk about that one because that goes into another point that I want to make as it relates to the benchmarking and majority voting system that they use for things like consistency. But thank you for asking. Yeah. Yep.
And the only other question I had was, this might be covered later too, is
Mhm.
I know you mentioned that RLHF on inference is the key thing that they do. I was just wondering what that means too.
So they don't actually do RLHF. They use reinforcement learning without the human feedback, and they have this whole policy optimization that just leverages the reinforcement learning with different chains associated with prompts. And we'll get to that. We're literally, I think we're about maybe a page or two away. No, we're literally right on the right page for it. So we're going to get to that in just a second. But yeah, we'll talk about that just a smidge more.
Thanks.
Yeah, you're very welcome. Now, one thing before we get to GRPO is that they do mention as well that performance can be enhanced with the inclusion of a small amount of cold start data. I don't actually think that's true, both based on what they say and what subsequent duplications of their work end up showing. And I'll get into why I think that's somewhat questionable as well. But ultimately, it's just one of those things that I noticed. Again, like little things about the language that I would personally find a little questionable there. But that all being said, let's actually take a second to talk about GRPO. Now, we're not going to spend too much time on GRPO. I originally thought I was going to maybe put more time and effort towards discussing it with you all. But given what I know now and given what I understand about policies and process versus outcome-based reward modeling, you don't really need to know too much beyond the conceptual of what's going on here, especially if you're not from a bit of a math background. This equation is honestly pretty gnarly. So I'm going to try and break it down in a relatively simple fashion where we're not having to think too much about each of the individual symbols beyond what's relevant for the conceptual explanation, right? So group relative policy optimization is just another type of what are known as policy optimizations, where we're doing this sort of post-training, almost this kind of alignment process towards getting the answers we prefer out of the model. Now, in this case, with the answers that we prefer are set up in these sorts of objectives, which are represented by this, which are represented by the final answer you get out of this equation, right? And there's a really good on the R local model or the R local llama Reddit board where they have this really nice breakdown, this nice visual around what GRPO is doing. And I'm going to reference this here and there as we kind of go through GRPO. But GRPO itself, if you really think about it, breaking down this equation is we start with this minimization of cross entropy. Now, this is essentially just a loss function. Like this whole thing is the loss function, right? Now, if you're familiar with like machine learning, what the loss function is essentially this process of us trying to minimize this sort of gradient descent calculation, this sort of loss that we use to find what are known as the minimas, or in this case, like the optimal minima, rather than this local minima. So this would be what we would consider to be an optimal minima versus this sort of localized minima of engaging gradient sense. And it's just kind of going down this sort of complex multidimensional plane. Now, right now we're only looking at it in like 3D space because we can only process 3D space on in a mental conceptual level, but you would be applying this sort of gradient descent loss function type calculation in any like type of multi-dimensional environment. It could have 200 dimensions. It could have 12 dimensions. The dimensionality is not relevant necessarily to conceptually understand it. It's just that we're going to understand it in the context of a 3D space where we're trying to take a value that might start here and then get it towards ideally here, but we might end up here instead, right? And that's really what the first part of the calculation is doing. It's what's known as the cross entropy function or the loss function that we are trying to minimize to make sure we get the best answer out of the model, right? That's pretty much what this whole thing from this min to this brace are really about, right? Now, this A value here as well as here is a bit interesting because it's what's known as the advantage. It's this calculation that we developed that kind of goes into the reinforcement learning element of why this calculation works for policy optimization. And to do a quick, brief, reinforcement learning type lesson, we use these functions to represent this Q-learning sort of reinforcement learning essentially environment where we take in a given state and an action being applied within that state. And that's really what classical reinforcement learning primarily focuses on, this Q learning process to find what is known as Q star, or the optimal value of Q. So the optimal value within the environment based on a particular state and action, right? Now, this A value is essentially calculated by taking this Q value, which I represent here more verbally as this environment. So this Q environment. So this environment represents the current state. So the current state within that environment, as well as the action being applied within that environment, right? So that's what this Q function represents here with this input S and input A value. Remember this environment and current state and action applied to it. Now we're taking that value and we're subtracting it from the separate function we're calling V, or the value function, which is essentially the value of the environment at a given state when we put in the current state. We apply the current state as the input. And this function normally in PPO, which is what a lot of comparisons end up getting made to for things like DeepSeek math. There are often a lot of comparisons between PPO and between GRPO in DeepSeek math, because they're trying to demonstrate in this paper that GRPO is just a better policy optimization. I believe there's a section here where they go over, from PPO to GRPO. They compare this PPO equation, which it looks relatively similar, but with the added difference that V function I just mentioned, that V function we were looking at, where this value of the environment at a given state, normally in PPO, we'd have to use a whole model to determine that value function. But in this case, for GRPO, they essentially toss out that model because we only need a reference model and a reward model. And I'll go into a little bit more of what those are in a second. I just wanted to mention that this value function is derived from the mathematics of the different reward values that end up getting initially calculated from the different chains, these different sort of chains of completions and prompts that then get assigned a particular reward where the advantage is then calculated, right? So we have these completions and these prompts, a reward is calculated for each one of them, and then an advantage is calculated. So that advantage is really what we're trying to take in. That is what that A of I is in the initial function we see here as well as here. And that A is just representing the advantage of an action taken on a current state, which I'm representing here as this function A taking in this input S of A. So it's just an advantage of an action taken on a current state where the current state and action applied are added in. And that's what we're ultimately calculating through the subtraction of the environment from the value of the environment at that given state, right? So ultimately what ends up giving us that value function that we're trying to calculate here is this sort of base average reward value of all rewards provided, which is essentially just the mean of all the rewards provided divided by the standard deviation of all the rewards provided, which creates a sort of normalization for what the total baseline reward value is, or what this V function essentially starts as, right? So with that being said, again, going back to this sort of really useful demonstration of it, we're essentially getting this advantage set by taking the initial rewards that are assigned by our reward model. And these rewards are then compared with this mean standard deviation across all of the rewards being set up here with these prompts and completions, right? So what we end up getting here is this situation where this Q state that we were originally talking about is just, for the sake of the reinforcement learning we're doing here, the given reward of I. So that given A of I value that we're trying to find, that reward at that current step. So that's just this R of I here that we represent as the environment at that current state with the current action being applied, right? So finally, when we want to calculate A of I here, that we leverage both in this part of the equation as well as this part of the equation, we're really, what we're taking is the reward of a given like set of prompts and completions, which a reward is assigned by the reward model we established earlier here. So this RM, or reward model, assigns a reward to this set of completions with this set of prompts, or this set of completions to this set of prompts, and so on and so forth. But each one gets calculated an individual reward, and that individual reward for the outcome that was gotten through this prompt and then this completion, right? That is where we end up getting this reward step, or the current environment with this state and action applied, which we then use to calculate this A of I. So, which is just getting the reward when we factor out this value function that we established through the baseline of all the different rewards calculated together with a normalization of the mean and standard deviation. So this z-score essentially is subtracted while taking into account that this new reward that was assigned for a given set of prompts and completions, which then gives us the advantage. And that advantage calculation goes into this loss minimization and amplifies it to then determine how much how much gradient descent we do, like how big of a step we essentially take from here to here, as an example, right? Now, finally, since we covered essentially most of what this function is, and this most of what we're trying to minimize here, we then need to take in what's known as the KL divergence. So if this is cross entropy, this is easier to refer to as relative entropy. And I'm not going to go too deep into relevant entropy, but for the sake of our understanding, this value or this calculation is essentially us minimizing the expected surprise of how far of a step we took. So when we're doing the initial step calculation, we don't want to go too far off of what we've already calculated up to this given checkpoint that we're currently working on, or this current point within the policy, this reference policy that we developed through this standard or supervised fine-tuning model, right? In this case, when we're doing the actual R1 training as opposed to like R1-Zero. So we're just trying to minimize the drift between what the current policy that we have versus the new policy we're trying to calculate, because this is where you run into the problem of reward hacking, which is this process where the model kind of gets stuck at one of these local minima that seems correct, but isn't really quite, like, we don't want it to be here, we want it to be here. Like, this is the area we're actually trying to head towards, but we went too far, so we completely avoided this downward slope and went right into this local minima that's not quite what we want. And we want to prevent that sort of issue from happening. We don't want to jump too far. Maybe we only want to go like half of this distance to the next point, where we can then do another calculation to see, oh, maybe we can actually go this way versus this way. So ultimately, that divergence calculation is just trying to offset the amount of loss that's done by not drifting too far from the policy that we know is acceptable and closer to what we want, without necessarily running into these other problems, like I said, with reward hacking or hitting a local minima or something along those lines, right? And that KL divergence is just accounting for the surprise of that jump and not trying to avoid it from being too large, trying to prevent it from getting too large. And again, even with that, we're still taking the minimum between these two, these values for the cross entropy. So we're still trying to take a minimum value, even with that, trying to offset that sort of jump for the loss function here. And we're just doing that for each grouping. So each of these particular groups of prompts and completions. Okay. Now I know that's a lot, and conceptually I tried my best to explain it, but we don't have that much time, so I'm just going to keep moving forward. Does anyone have any questions?
Can you put the link to the Reddit thread in the
Yeah.
Thank you.
Yeah, all of these links are going to be included towards the end. Especially I believe I can also have them put on the video. I'll talk to Caro about that moving forward. Yes, Philip.
Hopefully your audio works. Does your audio work, Philip?
No, it's not. I think he has a message in the chat. Yeah.
Read it out. You mentioned DeepSeek is better at coding as well as other STEM subjects. When I ask Gemini or ChatGPT coding problems, it's almost always right and cites Stack Overflow. When the statement better at coding is put through benchmarks, Does it omit sources like Stack Overflow, instead coding and reasoning from scratch, quote unquote? By from scratch, I mean using only what it knows from being exposed to programming languages and IDEs. Throwing out a pool of information seems counterintuitive.
That is an excellent question. And I think one of the things that we also want to consider in addition to that is that a lot of these metrics and a lot of this data for helping a model learn how to code is based on things like code challenges, not actual software development in a lot of cases. And while there are benchmarks that do test actual software engineering, like SWE-bench, which are covered for R1, we still see, and one of the problems they do highlight at the very end of this paper is how they could have done a bit more, since I know like right at the very end when they're in the conclusion here, because I do think it's worth covering this relatively quickly. Due to the long evaluation times, they ran into problems with large-scale reinforcement learning not being applied extensively in software engineering tasks. And that was just more of a long evaluation time issue that they had encountered, where in the future, rejection sampling will probably be done on software engineering data or incorporating more asynchronous evaluations during the R1 process to improve efficiency. But it might seem counterintuitive in that sense to continue to sample, to reject certain samples of output. But sometimes the data just isn't really particularly well put together or isn't really representative of the task you want to achieve. Sometimes it's just there's a lot of data filtering and cleaning that goes into actually developing these models initially. So it makes sense to remove certain things from say a Stack Overflow where you're trying to remove snarky responses on certain software or certain software engineering questions, right? And followed by certain answers. So you do probably, in a sense, because of that, end up losing relevant information that could potentially be used to help these models in software engineering and therefore to generalize better. But it's also kind of this inherent trade-off of helpfulness and harmfulness that we often run into with machine learning, deep learning, LLM type tasks, where you're ultimately still wanting to make a good model, but you also want to make a good model that doesn't make an engineer cry every time they try to help them with a problem, right? So that's one of those things where I think it's partly the alignment in that sense, but also partly the desire to not take in particularly crappy data, and partly just the process of the difficulty that goes into data cleaning and data validating the quality of data that you use before actually putting it through. Does that answer your question, Philip? All right. So I'm going to go back up. Kind of skim through a little bit of here. So again, we're going through the reward modeling. We essentially have an accuracy and a format reward that is a part of this reward modeling process. They don't really plot an outcome or process neural reward in the model for developing R1-Zero. So it's primarily now, for training R1, I believe they applied the sort of outcome reward modeling as opposed to process reward modeling. And there's evidence to suggest that process reward modeling from the R-star math paper, as well as even if we go so far back to let's verify step by step, there is evidence to suggest that process reward modeling is generally better than outcome reward modeling. Now, again, kind of like the policy optimization, I don't really think it's going to matter in the long run, just because of the bitter lesson. I don't know if you're all familiar with Richard Sutton's The Bitter Lesson, but if you're not, amazing read. It's only 2 pages. If you are even remotely interested in AI or reinforcement learning, you must read Richard Sutton's The Bitter Lesson. I think it should be mandatory reading just so you understand a fundamental element of reinforcement learning, which largely boils down to this idea that if you just throw enough compute at the problem can essentially solve itself. That's really a TLDR type reading of it, but we often create these sorts of human-centric and human-biased sort of processes to figure out an answer that we think a model would be able to follow, these sort of symbolic systems of understanding how logic can be essentially mimicked in a given domain. But what ultimately ends up beating that out is just throwing more compute at the problem. And really, the Bitter Lesson just highlights how this consistently happens again and again throughout the field of AI, where we run into this, just once we figure out how we can scale compute, we can just solve the problems that we thought were nearly impossible when using more human-centered approaches to solving problems, because a model can just train itself to solve the problem better than we can get the model to learn. Well, maybe not the best explanation of that, but basically the model can teach itself the enriched understanding of the problem and the solution to the problem, which is something that we have our own biases towards, and those biases don't often adequately fully capture the rich space in which the problem and the solution can exist in. Yes, thank you, Aaron, for thinking that. Again, really great paper. Highly recommend you read it. But that's kind of one of the problems that I have here with ultimately focusing too much on policy or optimization, or too much on the type of reward or type of reward modeling process. Like ultimately it's just baking in biases that we're still having. And there's subsequent evidence after this paper came out that suggests that it might not even really matter. And in my opinion, like in my intuition, it feels like it wasn't going to matter to begin with. So although it's important to kind of get an idea about policy optimization and different types of policies that you could use, don't focus too much beyond the conceptual at this point. The PPO is probably going to become good again next week. You never know, but we're not going to get too deep beyond that. Anyways, that's the last we're going to talk about, policy optimization. Okay, if you want to learn more about the policy optimization specific to R1, just go to DeepSeek Math, this paper here, and you'll learn as much as you want about PPO versus GRPO. Okay, so with that being said, let's go back here. Where were we? There we go. So ultimately, they're limiting their constraints to the structural format, so they don't really do any content-specific biases, which was kind of what I was talking about earlier, such as mandating reflective reasoning or promoting particular problem-solving strategies to ensure that we can accurately observe the model's natural progression during the RL process. Which is to say that like the model will just naturally like teach itself. We don't really need to add anything else on top of that, right? So again, we see these neat little like charts and like, oh, R1-Zero is surpassing like O1. We have that pass at 1K and const 64. I'll get to both of those in a bit, but just to pass at 1 is solid. Constant 64, in my opinion, is kind of questionable. I'll explain why in just a bit. But ultimately, the self-evolution process of DeepSeek-R1-Zero is really kind of fascinating, and really the demonstration of how RL particularly can drive a model to improve its reasoning capabilities autonomously. And ultimately, that is something that I think is really the biggest takeaway from this paper, because of how R1-Zero just naturally acquires the ability to solve these increasingly complex reasoning tasks by leveraging this extended sort of test time computation paradigm that we found ourselves in. And you get these really interesting, like weird emergent behaviors, such as the model's reflection, this sort of model then revisiting and reevaluating its previous steps, and this general exploration of alternative approaches to problem solving, which just kind of they just arrive spontaneously. It's really kind of fascinating. You get these weird aha moments from DeepSeek-R1-Zero initially, and that's where they kind of have that sort of wait. This is the way I can flag this here. Like this is, let's really think about this for a second. I can let me try this. Like the little things like that feel very human, a model will just spontaneously engage in when you teach it reasoning, which is just fascinating. And people are literally like duplicating this for like $30, $3, but essentially this sort of same aha moment in narrow task domains where they don't have to spend nearly as much compute, but they can still get really like insanely good reasoning performance on given metrics. Right now, with that all being said, part of the reason I think we don't really hear too much about R1-Zero, in spite of why I really think it's what makes this paper interesting, is because of the fact that it has what the model creators considered poor readability and language mixing, where basically the model kind of mixes languages a lot, like Chinese and English, and its thought process isn't that easy to read because of that. So you have this sort of problem where it's not good UI for a user who just wants to get a model that'll explain to them its thought process, which is part of the reason why they developed R1 after R1-Zero, in addition to the fact that it's just kind of productizing the model a bit more, in my opinion, like making it more easy to work with for somebody who's maybe operating with just English or just Chinese, or something where you don't want to have to deal with too much complexity in deriving the answer and figuring out the reason behind it, right? So that's where they kind of get into this R1 reinforcement learning with a cold start, where we have this sort of cold start of initially doing the supervised fine tuning to take the base V3 model to an instruction sort of model, like a Q&A type model. And then from there, applying that sort of R1-Zero training, which gets the model to do that sort of reasoning. So we take it from instruct to reasoning. And that's what kind of, we just kind of repeat that process with more supervised fine tuning, and then an additional reinforcement learning training on data generated in combination between, I believe it was R1-Zero and the base V3 model, for different sets of tasks, depending on how related to reasoning or mathematics or general sorts of topics like that versus, or less general sorts of topics like that versus things like language or Q&A or like factual accuracy, which are different sets of topics. Yes, Aaron, you had a question.
I wanted to shout out Vinu. Prasad just shared the fireworks breakdown on DeepSeek. So
Nice.
that's in the chat. I do have one question though about language mixing. Like, is it because primarily, if let's say you're not Chinese American or don't speak like Chinese and English, like, is that sort of like the results that they got from language mixing? It's just, I'm a little bit confused because I'm wondering, like, does that apply to all other non-English languages in that benchmark as to like why they developed an evolution of that to kind of correct it so it's not doing, at least the way that I like to see it as an Asian American is like, oh, well, that model is just code switching between languages. Like, I'm Filipino, so I speak Tagalog and English, we'll call it Taglish. Like, is it just avoiding that so that the models themselves are just speaking purely in one primary language? And sub question / comment of why I say that at MetaConnect, you know, they talked about, and we actually discussed this at our last paper reading on Llama's paper, Llama 3, like there's a lot of investment by Meta specifically on let's say like Indian languages, right? So anything that has a good amount of language diversity. So yeah, if you could just like break down like why it's actually important and how to clarify like what's the like gold standard or benchmark we're trying to go for, not just so that it's clear to any researcher throughout the world, but is it privileged to only English data, which I think for a lot of other people, especially those from underrepresented communities, like, oh, well, this is just not very accurate because it only works for, you know, maybe the 5 most spoken languages in the world that have the most data. So accuracy becomes like a question. Does that make sense?
Yeah, kind of. Yeah. So on a few different levels, let's break that down. So first off, the language mixing itself, that seems to be a more discrete sort of, like what I noticed, for examples, were like, it will solve this portion of the problem in English, but then it will switch to Chinese and do like a good chunk of the problem in like, I think Mandarin. And then it'll go back to English maybe to like provide the answer, or maybe it'll just still be in Chinese, like things like that, where the consistency of when it goes to one language versus the other and why it's doing that, it makes it kind of hard to just discern through unless you say know both languages. So it is a kind of code mix, code switching in that sense. You're not wrong. I just think they find it to be a bit unwieldy. And it also didn't, they got better performance out of just having R1 go through more rigorous sort of cold start, supervised fine tuning process in addition to the reasoning reinforcement learning, where they ended up getting better performance on that. So I think that's part of the concern. I do think you're absolutely right about a lot of internet data is mostly English, like the overwhelming majority of it in a lot of cases, regardless of the domain, tends to be in English because of how the internet was originally created in the 80s, I believe, in the like DARPANET in the United States, and then it kind of popularized throughout the 90s, and then it became more of an international thing throughout the 90s and 2000s and 2010s. So we're only really starting to see a lot more non-English data really starting to make up the bulk of like new data creation. As more and more people get online and get onto the internet. So you're absolutely right that that plays a role in it. In particularly for the case of R1 and R1-Zero, I know that they initially trained their DeepSeek v3 model with primarily English and Chinese data. So it really, a lot of it, I think, also boils down to not just what the internet has, but what you're putting into the model. And it just so happens a lot of what you're putting into the model will be probably a combination of your own language, if you are not from an English speaking background, in addition to English in a lot of cases. Especially from China, I know they have a very active internet culture, like a very interesting like netizen sort of approach to the internet, which allows there to be a lot of Chinese data available as well, and solely Chinese data versus like a mixture of, say, maybe like Mandarin Chinese and a bunch of other languages that might be harder to parse from like a data cleaning sort of data filtering level. So that's probably part of it as well. So I think it's kind of just a combination of those different factors that ultimately kind of lead to what we're kind of seeing in particular with these models, but also on a broader level with model creation and on the whole. Does that make sense, Aaron?
Yeah, sounds good. Thank you.
All right, thank you. So with that being said, let's go to how much time do I? Ooh, yeah, I'm running low on time. Probably should have allocated an hour and a half to this, to be honest. So yeah, they make this distinction between reasoning data and non-reasoning data. I don't think it's the best distinction. That was part of my confusion. I didn't really know of a better way of conveying it, but that's the distinction they make ultimately. And they do try to apply reinforcement learning through all of these different scenarios between these non-reasoning scenarios or these reasoning scenarios. And they have this total set of 800K samples that they use for the two epochs on fine-tuning their DeepSeek v3 base. Where once they've done the initial supervised fine-tuning data collection from the reinforcement learning, they essentially like do the same thing twice, but with that additional cold start with supervised fine-tuning. So they just add back the supervised fine-tuning for R1, and then they go through that whole reinforcement learning training process. Then they add back some more supervised fine-tuning data and go through another reinforcement training process, which does help to distill out a better performance in a what I believe to be a faster time turnaround. Even though it takes a few more steps in their pipeline, it does seem to achieve better results for them to take that sort of double process. And that's what they then use to distill their R1 variant models using combinations of the Quen models as well as the Llama models for their R1 distillations. So just wanted to point that out as well. There's also the experiments where they cover benchmarks, and a lot of these benchmarks are just like the classic ones, MMLU, C-eval. Well, C-eval and CMMLU are more Chinese-specific versions, if I remember correctly, of these, of at least MMLU for CMMLU. You got if-eval, frames, GPQA, Diamond, Simple QA, and these it basically it's just benchmarks and like judging, like models judging other models for determining these benchmarks. And they go into a significant amount of detail for the results on these benchmarks and how they go about conducting these benchmarks. Like Aaron, specifically for your question related to benchmarking and evaluations, this is really like the evaluation prompts, like this whole like section for experiment, really like the beginning of it covers a lot of that. For example, they use Simple Eval, the framework from OpenAI for MMLU Redux, MMLU, Drop, GPQA Diamond, and Simple QA. They're evaluated with the prompts from Simple Evals and that Simple Evals framework. So you could probably pull those in from there and essentially duplicate that effort if you were able to rent some cloud GPU and then just kind of host the R1 model there and then run through the evals framework on that same hosted environment. So there are things like that people can do on the evaluation side to check these models and to corroborate the results that come out of them. In addition, they do evaluations against these different baseline models, like their base model itself, Claude, GPT-4o, O1 Mini, and the latest version of O1. They have ran into a bit of challenges because of the AI restrictions for O1 API testing in mainland China. But beyond that, they did a bunch of these evaluations. One of them is PASIC-K, which I know somebody had asked about that earlier. So PASIC-K is basically out of how many times when we prompt this model, so K times, out of the K times we prompt this model, how often does it respond correctly? So the goal with PASIC-1 is like, if I prompt this model once to get an answer, does it respond correctly in that one time that I prompt it? That's what PASIC-1 means in this case. So basically, when I prompt the model, does it give me the right answer when I prompt it that first time? If not, it fails the PASIC-1. If so, it passes PASIC-1, right? And that's PASIC-1 pretty much in a nutshell. In my opinion, pretty much everything other than pass at 1 to pass at 3 is just nonsense, in my opinion. Because if you're prompting a model, you should probably get the proper output within the first like 3 tries, rather than going into like 8 or 12 or 15 like people did back in the day. They also introduced this additional benchmark for consensus, like that const, 64 const, where it's just out of the 64 times that we prompted the model, how often did it get the correct answer the majority of the time, which is a better metric, in my opinion, for focusing on things like consistency. But I would personally prefer something where we're just measuring consistency for all the answers provided, as opposed to only a majority. So like out of 64 tries, how often does it get all 64 correct? Like, that's really the focus I want. I understand it's a bit more of an intensive evaluation, but I think one of the things holding back models from doing a lot of valuable tasks is the problem of consistency due to things like hallucinations and the statistical inference that is ultimately both a bug and a feature of LLMs, right? So that's my own 2 cents, my own little soapbox on evaluation metrics. I wish we were all collectively a bit better on focusing on consistency in addition to accuracy, but that's just my opinion. But yeah, like I said, we go through all of these education-oriented benchmarks. We go through these enhanced STEM-related questions where we see a higher performance from R1 as a result of its, like I said, its enhanced reasoning for STEM-related questions. We see generally the R1 model excelling. And again, you can double check these evaluations on your end. You can see what they highlight relative to what DeepSeek outperformed on versus these other competitive models in the closed/frontier space. So just things to keep in mind. On math tasks, again, we see R1 really demonstrating high performance that is comparable to or on par with O1. While not necessarily like beating it in a lot of cases, you see essentially a pretty consistent sort of performance from the distilled model evaluations, right? And ultimately, like distilling R1's models outputs does create a better result versus just training a better result just training directly on the directly training reinforcement learning on the given models that were initially brought in to be used for the distillation. So using that RL inference process for GRPO versus just distilling down R1. Distilling down R1 is a better approach to take for better results, in addition to being less costly. So that's another thing that they cover for distillation versus that reinforcement learning process. Again, they focus on they also talk about what some of the unsuccessful attempts for trying to train R1, including that they avoided a process reward model just because it has what are ultimately 3 main limitations. There's a challenge to explicitly define a fine-grained step in general reasoning. Determining whether the current intermediate step is correct is for a challenging task. And once you introduce process reward modeling, you run into a problem of reward hacking that tends to be pretty pervasive. And ultimately, retraining the reward model needs some additional retraining resources, which just complicates the whole pipeline process. They also tried Monte Carlo tree search, which worked really well for AlphaGo and AlphaZero. When those models originally came out for Go, Monte Carlo tree search is useful in those narrow domain sets, but ultimately this approach encounters a lot of challenges when scaling up the training and generalizing it beyond a given narrow domain, where token generation presents an exponentially larger search space that you have to deal with. And ultimately, the value model directly influences the quality of the generation. And if you're using the same model as the value model, you're kind of going back to PPO and the problems that come in with having that whole separate value model, which is where you fail to get, or it becomes a lot more challenging, I should say, to make iterative improvements, because having a well-trained, fine-grained value model becomes harder within that given space that you're having to work with. So while Monte Carlo tree search can improve performance during inference, when paired with a pre-trained value model, iteratively boosting model performance through that self-search kind of remains to be a significant challenge, right? So ultimately, some of the bigger conclusions is they're going to be working more on addressing language mixing, prompt engineering. Apparently, R1 it actually does a generally across the board worse when you're doing few shot prompting. Like the performance consistently degrades, which I found was pretty interesting and questionable. I wasn't really sure why that should be happening, but it's something that they noted here, which I thought was interesting. And ultimately, large scale RL has not been applied extensively in a lot of software engineering tasks, as we kind of discussed earlier, and filtering out the data for like software engineering specific tasks versus like code challenges, I think is going to be more of a problem as time goes on, because ultimately I think they're two very different skill sets, and working on an enterprise scale application is not the same thing as solving a leet code or code forces type question. There is certainly overlap, there's obvious overlap, but it's not the same it's not the same level of problem at the same scale, if that makes sense, right? So that's pretty much the paper in a nutshell. I'm a little bit over time, but I have a bunch of other stuff as it relates to going over some of the different replications. If anybody's able to stick around, I can start spending a quick bit of time just kind of going over this. For example, this UC Berkeley student who managed to reproduce the aha moment for R1-Zero in the countdown game. So that's another thing that we've noticed from other people replicating the results from R1. For narrow task domains, you can replicate the results for a fraction of the cost for the RL training. In this case, under $30, but in some cases as low as $3 on much smaller models, where you can get much higher performance on that particular task. And it's really kind of, in my opinion, getting to the point where applying reinforcement learning on a given LLM in a narrow domain where you have this sort of reward signal, this like yes or no, right or wrong answer in advance, you can essentially get human level or superhuman level performance from like a 2 or 3 billion parameter model. That's really what we're starting to see from these replications. Like, again, we have this other example here. Well, maybe not this one, actually. That's like questions being answered on by the UC Berkeley student. But we have this other replication where they use RL with verifiable rewards to incentivize vision language models to learn like general counting abilities. So this 2 billion model can get like nearly a 99% on this same task, where a 72 billion parameter model scores at a lower performance. And they have this whole chart about it. But the broader point that I'm trying to make here is that this is really the more interesting element of R1, where we start to see that these models are like even these smaller models in narrow domains can surpass these much larger ones in these given task domains. But the reason why that's able to happen, in my opinion, is that we're only just pulling out what's already in the LLM. We're not actually getting them to learn anything new necessarily, as much as we're trying to drag out with reinforcement learning the data that already exists compressed within that model, and then getting that model to apply that data that already exists within it to then achieve better results, which I don't necessarily think is going to lead to what everybody considers to be AGI, but I think it's really interesting because it ultimately will give us better models, at least in the short term, if not in the long term, giving us something that could be comparable to a human or surpassing a human on a variety of different like economically valuable tasks or domains. All right. So yeah, that's pretty much all more or less that I have to add here. Any final questions before we end out?
Oh yeah, can you share the Reddit link again?
Oh yeah, absolutely. I can drop that in the chat as well. Okay. Yoink. Thank you, Ray. Good seeing you as well. Oh, by the way, I noticed.
Oh, I had another side note. I don't know if you have comments on this, and I mean, we can stop recording. It's
Oh, let me actually turn off the recording.
About, like training. So does China, if they didn't have access to H100s, they optimized this, but did they really buy like H100s from Singapore? So this was actually and I'll paste in the chat just because other people were asking for it. It was this was actually mentioned on the All In podcast, with David Sachs in particular. So you know, they were kind of speculating, like, do they have access to this? Like, how many actual GPUs did they use to train it? There's a lot of questions about distillation. You know, what did they actually quote unquote steal from OpenAI, and did they really train on a large number of like GPUs? Given that, like, if China didn't have access to it, they leveraged Singapore for like larger data centers, and then the question becomes largely like in like the research community, everyone's kind of banking on it. Is Meta positioned in a way that everyone's just trying to bet on them if it isn't OpenAI to be Gemini and everyone else? Because, you know, there's, again, we talked about this earlier, it's totally off topic of like US versus China is that larger debate. But if I'm not thinking about the geopolitical nature of it, I'm just really thinking about, so did they train somewhere else with a larger like number of GPUs, depending on whatever country it is, I don't really care, but is it truly like that much more performant than what OpenAI may actually be developing internally that they haven't released? Because if you see, you know, their head of research tweeting about it, they're like, oh, this is great. You know, they found what we already found in our research. Because I think people are sort of thinking, well, Microsoft's not loyal to OpenAI. So people are thinking OpenAI is dethroned, which I know Sam Altman personally. I don't I know him well enough that I don't think he's worried as much as other people are. And it's the same speculation you had about Jensen. But yeah, that was my main question. Like, should we be worried about this as much as people say we should, because it is that much more performant? And is it true that they used comparable like amount of GPUs to, run all of the training on the data that they have?
Okay, so broadly speaking, I'm not worried. I think a lot of people are worried in ways that don't really make sense or are kind of irrational.
Yeah.
I think people who are actually in the know for a lot of this it's kind of a situation where cooler heads are and will prevail. Like you said, I'm sure Sam Altman is aware of what they're doing, and I think one of the first things that he thought, in addition to one of the first things that Jensen Huang thought when this model first came out, even the V3 version necessarily, we're not even talking about R1, was like, hey, look at all this cool stuff this lab in China did. Look, all these neat optimizations. I want us all to get together, spend the next few weeks kind of digging through this paper, figure out exactly what they did, and we're going to replicate it on our end to provide to our customers. And I think that's really one of the bigger takeaways they had on their end, looking at it from companies like NVIDIA or like OpenAI. It's like, hey, this is really neat. This is cool. I'm glad we have interesting competition going on now. Like, this is where it actually gets kind of fun and exciting. And we're going to have a really interesting time kind of digging through these innovations and leveraging them for our own technology. Thank you very much, DeepSeek. I think that was probably the bigger takeaway.
Had that is what I assume.
They probably had a lot of it, I would imagine. I don't think I think there are certain things they may have already had, certain things they maybe didn't try with certain applications. Like NVIDIA probably didn't have like a lot of the threading changes that were done by DeepSeek in order to actually get the GPUs to run more effectively, their H800s to run more effectively. So I think there was probably some open questions, at least in NVIDIA, for example, about, hey, let's maybe try this these threading changes. See if we can figure out the threading changes they made so we can get our GPUs to go faster. Let's hook it up to CUDA and then just give it to sell it to our customers, right? I think there was probably some of that went on. I think in the case of OpenAI, it's probably like, oh yeah, that's really neat. We did a few of those things. That didn't work out. That's an interesting thing you all did there. Cool. That V3 model you developed for like 5.6K for that final run. That's pretty cool. Some of those changes, like that multi-headed latent attention, which I didn't get to go too deeply into, but like is one of the innovations that really optimized V3. That was something that a lot of people were interested in, and was an approach that could have been taken. The training schedule for how they parallelized the actual training of the V3 models, another thing. There's a lot of what makes R1 interesting is really in the V3 paper. And again, it's not a hard requirement to read it, but like a lot of the cool and interesting optimizations where they get the price point down significantly lower is really in that V3 paper. And I think that was more interesting for a lot of people initially. And then when the market overreacted to R1, everybody and their mother started getting into R1. Even though like I literally planned this talk like a day before. Like I originally announced this talk I planned it. I set it up like a day before the market went up. And I'm glad I did it like a week or two later after that, because it allowed me to kind of like separate the wheat from the chaff as it relates to this paper.
Because there's a lot of noise, and then
there's a lot of noise.
Maybe the one thing I'll mention in the podcast, which I just dropped the link in the chat, so everyone knows David Sachs. I went to his hackathon for Grok.
By the way, Aaron, it is still recording. I hope you.
Oh, sure. No, it's fine. I think you can record it.
Cool. Just want to be sure.
What I will say is, so David Sachs, I mean, everyone knows I'm a hard-bleeding Democrat. I'm a founder of Tech for Obama, is my boss. David Sachs is like hardcore Republican. He actually is very detailed in all of his podcasts. I may disagree ideologically on some politics, but he's really good at breaking down some of the differences within this paper and like what's at question in the debate about data. The one thing I'll mention that we didn't get to talk about today was, what will quote unquote replace the transformer model. Is one. And then the second one being, they talk about PTX, which basically what DeepSeek did was bypass, I guess like NVIDIA's moat of CUDA. So that's the interesting part, which we didn't get to talk about today, but just for people supplementally that are observing this space, I would definitely check out the podcast and like obviously do your own research and run your own evals as you look at any of these papers coming out.
Yeah, and I will say, for what it's worth, from my understanding, given the geopolitical situation and certain elements of AI that go back to national security, there does seem to be a broad sort of like nonpartisan, bipartisan consensus on the topic of AI, which I find fascinating from my experience dealing with people in the US government and from understanding their kind of sort of takes on some of the more recent events that have been happening. That's kind of one of those things that I just think are just broadly interesting as it relates to the broader question about the R1 and what it does to the industry. And that's one of those things where ultimately I kind of agree with you, where it's like, it's more so interesting for me to see how much we can get out of RL before we ultimately need to start thinking about the architecture again, because really that's really, I think, the thing that matters the most, because we really need to think about what's coming after transformers. What can we get to be like the architectural innovation that allows us to really take what we currently have and go that next step beyond, that addresses some of the fundamental problems with the architecture, like hallucinations were a big one that I brought up during the paper talk. But like things like that, where you're running into these sort of bottlenecks of consistency and this ability for these models to generate reasonable, like consistent outputs for the same task or even the same prompt. So yeah, ultimately it's going to be interesting more so to see where that goes in the long run, because ultimately I think reinforcement learning, again, it's a situation where it's really bringing forth what the LLMs already had in them, but it isn't necessarily making the LLMs necessarily smarter or better, adding new information. It's just dragging forth out of the models what they were already capable of doing, but just didn't have a process to find in a consistently clear fashion or relatively clear fashion. So, but yeah, I agree with you broadly. I think this is an open question about a lot of different things, like the whole price point too. That's another thing that I could spend hours talking about, just how ultimately the 5.6 number is nonsense, but not for the reason a lot of people think, because it's really just the last training run of V3, their base model. That's where that number originally comes from. So anybody associating it with R1, it really, like, they're spreading misinformation, because literally it's just that 5 point, like I think it was 578 number for the last training one of the base model of V3. That I buy. That I could totally see being the case, but like we have to then not count for the ablations. We have to then not count for any efforts made after the fact in that post training I was just talking about. We then have to account for the fact that all the technology and research that went into the DeepSeek math paper, where we're just testing it on a 7 billion model before we try and scale it up and generalize it more. We have all of these intermediate steps that a lot of people aren't considering. And I even have this paper. Let me share it real quickly. I didn't get a chance to talk about it directly during the paper here, but basically semi-analysis does a really great breakdown of what the cost actually was more likely to be. I think they estimated it was going to be like $1.3 billion, like to be more accurate to what the total spend was on developing R1. But I thought that was pretty interesting. But yeah, like again, for the longest time, prior to reading the DeepSeek V3 paper, I tried to track down where that 5.6 number came from, and this is literally where it came from in the V3 paper. Literally, like the GPU, the 8100 GPU hours going into the final training run, essentially, of the V3 base model. That's where that number's from. So anybody saying that it only cost 5.6 million to create R1 doesn't know what they're talking about.
Yeah, exactly. Aaron Tullis asks, would you compare DeepSeek's advances to improving our ability to query the LMs if they were databases?
Maybe not like databases, but doing better querying of the model to get a more likely response, yes. Because again, we're still lacking that inherent determinism in the model's ability to select the correct answer, because it'll probably give you the right answer, but it also might give you one that seems totally off base, even though you're using like the same prompt you did earlier with only like a minor adjustment on the temperature as a simple example, right? Like there's still an inherent lack of determinism due to how these models fundamentally operate on statistical inference. So yeah, you can think of it like querying the model with a better prompt or a better set of prompts that lead to a more correct answer. But ultimately, the fundamental limitation is that hallucinations with this current architecture will always be present. It's just we're going to see less of them over time down to a certain point. Does that make sense? I will assume so. But yeah, I had a bunch of other paper. Oh yeah, this was another one that I failed to show right on time. But like, that's another thing a lot of people are kind of underestimating. Like DeepSeek and Alibaba have been like catching up for a while now, and they aren't the only like labs to do this. Like they're just the ones that a lot of people have been paying attention to recently, given the major like changes in the news. And I really like Peter Gustev's like posts on LinkedIn. He has a lot of like really helpful infographics. So definitely follow him on LinkedIn if you can. But like he developed this whole like chart for Elo score on these different models for the chatbot arena. So yeah, again, like a lot of people have been catching up to OpenAI lately, at least in terms of what has been released from them, in addition to all the other frontier model labs, because a lot of what they're doing isn't really that compute intensive. It's more like the secret sauce that kind of goes into creating these models. And to be fair to DeepSeek, like that's literally their owner company, like the company owning and funding them, High Flyer, that's literally their bread and butter, because they're all just a bunch of, like, at least in High Flyer, they're all just a bunch of quants, right? And quants, I don't know if anybody here are familiar with quants, but they're basically quantitative researchers, and pretty much their whole job is to work with complex mathematical systems and optimizing and tweaking those systems in an effort to make them just that little bit more performant, or able to maximize in volume or profit in some weird esoteric ways that allows you to generate like potentially billions or if not millions more in income. So it's like that's literally what quants do on a regular basis. So the idea that they would be able to get into the AI game for fun as more of a side hustle and leverage the spare GPU compute that they weren't using for their regular hedge fund trades to then create this like top of the line O1 level model and then just release it to the public for free and then host it on their own application for free. You're dealing with like really high tier, like elite operators when it comes to STEM fields at that point. Like a lot of people just do not give quants generally enough credit for how like absolutely badass they are at STEM and what they're capable of optimizing in STEM because of this very diverse background with a lot of broad overlapping with the more common AI researcher and engineering skill sets that you often see. So I just wanted to take a second on that as well, because I thought that was really that's really something we should all be more cognizant of as what quants are capable in STEM relative to, say, a software engineer who does software development, or even an AI researcher or engineer. Quants are badass. Like they are some of the elite operators of STEM that are often the unsung heroes who are very specialized at this task that they are working on and doing. So. All right. So does anyone else have any other questions?
Do you have any good links on self-research? I ask this because the project I'm doing for the UC Berkeley's LLM agent advanced course, I'm trying to build another poker bot, but it's for Filipino poker. And like the benchmarks are Chinese poker, but you know, the main researcher I'm looking at, well, he got poached by OpenAI's Noam Brown, and his work was actually focused primarily on RL, but has now since then pivoted obviously towards general models. But I think the thing that I was basing a lot of my research on is like, I don't want to say debunked by what you said with the limitations of self-search, because everyone's just kind of stuck at, you know, Monte Carlo. So I'm trying to find alternatives and like really digging deep into like, what does self-search actually really mean? But yeah.
Well, in that case, then I would maybe consider like looking at the different types of self-search, because I know they highlighted things like beam search and like different variations on like different sort of tree searches along the lines of Monte Carlo. So it's defunct in the context of developing general reasoning, but that doesn't necessarily mean that it lacks application in like Filipino poker, right? And I think a lot of Noam Brown's work, particularly on poker, was pretty foundational in terms of developing these models that we really see sort of setting these standards in games that later then lead to really these advanced sort of developments in the field that we're in now. So I wouldn't be again, like I'm sure you've been looking at Noam Brown's work. Like first off, I also want to say really big fan of his as well, and really great researcher. Anytime he talks, like it's like him and Jim Fan, who I feel like will often drop some real bangers of posts on different social media platforms that I feel need more attention, because these are the people actually working on this tech that you often don't get to hear too much from because they're not like the faces of their companies respectively, but really interesting like researchers and engineers nonetheless. And I just really like, it's always interesting and fascinating to hear what they have to say. But going back to the self-research question, a lot of it I think just kind of boils down to like doing what you're already doing, for lack of a better phrase. Because the thing is, like, going into the weeds of like your particular problem, it feels like kind of going back to the original like elements of search that were kind of pioneered by a lot of these people. So, but yeah, I mean, just kind of staying in the community and kind of digging into some of that older stuff could be helpful, and how it can then be applied to Filipino poker. I'm sorry if that's not a great answer, Aaron. I think it just kind of, you're focusing on a hyper-specific domain, and there's already a lot of work, I think, built around focusing on domains. So I think you'll probably figure something out for that.
There's like Chinese poker. No one's applied it to ours. And like, so the reason I asked too is because Strong Compute, which is a Y Combinator backed company, I did their hackathon last year, which was on chess, so GPU chess. But the person that won just trained their own data the whole time, and there was nothing interesting that they actually did. No offense, and they were great. And they worked in crypto for a long time, and I talked with them because they were just having fun. But for everyone else, I think that were hackathon participants prior, they're actually a bunch of students who were like doing what we think about in terms of sentiment. So that aha moment that we see, that people are really paying attention to that. That's something students are actually doing a lot for, chess hackathons. And so I was thinking, well, could I apply that to poker, because that hasn't been done? And a lot of my friends, one of them actually was one of the few poker players that played against Libratus, which is in Nolan Brown's work. So it's more interesting because to me, it's a step towards AGI, but I feel like a lot of that work is forgotten, where I'm like, oh, yeah, still think there's something there, but we don't have new benchmarks around said games because we're so focused on generalized models. But I feel like that might get more interesting because it's much more realistic, to me personally, because the human brain is so complex. Like anyone saying that this is going to be AGI, I'm just like, no, there's an entire thing capturing in terms of thinking. Not everything can be done in silico that's in brain. There's a lot of like advances that I think still need to be made, and there are new benchmarks I think people want to set, right? Just like the same reason why people are saying, oh, it's more than just a transformer model. There are new ways and new innovations, but it's worth looking at like, what do we know now, and then revisiting the fundamentals. What new things can we kind of invent? So that's the reason why I asked, because I didn't realize like, oh, self-search. I was like, oh man, this would make the research I'm doing kind of seem like it's moot, but I feel like there is still something there, but I haven't found it yet. So it's, my intellectual curiosity.
Yeah, and honestly, like the reason why I say it's moot isn't necessarily because like work like that it makes that work irrelevant as much as it makes like a lot of the generalized reasoning work that's going on right now just ultimately boils down to like scaling compute. Like that's what I'm talking about more than anything. Like that's that sort of like, if we do by some miracle achieve AGI with LLMs, it's going to be through sheer like just pounding compute and brute force. Like that, I don't think that you're going to get anything. We're going to get anything. We're not going to really be able to get AGI with this paradigm through some sort of like tweaks around the edges type optimization on that current architecture. It would just be just pounding compute and data at the problem. So I that's why I say that in that regard, it's kind of moot. But in terms of like the day-to-day sort of deep learning or machine learning work, like that, the groundwork that really pushes the field forward, at least on certain domains, I still think the work that you're doing, for example, is extremely important and necessary, because it gives us more opportunities to explore this sort of space that we're in and leverage techniques that may have already been developed, or find new ways to apply techniques that might have more interesting use cases later down the line. I think a lot of the techniques that we're finding now are, like, at least in general reasoning, were figured out through that process of developing solutions for both machine learning and then later down the line deep learning, and really kind of just scaling those up. So you might figure out something as it relates to working on Filipino like poker that ends up becoming really relevant, or an aspect of it inspires someone else that becomes extremely relevant to the next level of AI models, right? Like, or to this new architectural paradigm, because of this certain way that you may have approached search versus somebody else who had came before you and were applying it in a different way for a different problem set with trying to accomplish a particular task, right? Does that make sense? Because I feel like ultimately it's just one of those, like, you don't get too bogged down in like what people consider sexy on the day-to-day. It's really more about doing the work consistently, making innovations, accomplishing things, and just kind of establishing precedents and corroborating creating consensus through like coming to independent conclusions that can resemble other, like that's the scientific process. Like that's, the field is moving too fast right now, and one of the easiest ways I get the equivalent of peer review is just seeing other people come to the same conclusions from independent labs, right? And in that sense, you can essentially do that for this for these different fields.
Right. I mean, it's more than just at the end of that hackathon achieving like the ELO score, which is just, again, it was just like you said, scale and compute. They said the most interesting was sentiment, right? And as we're seeing, like, oh, this doesn't apply to all the languages that we can think of in the world. It also hallucinates. So it's actually much more complex, which is why I think it is still worthy of that work, even if it's not like, you know, coming out with some other said, you know, generalized benchmark. It will still iterate in the field. But anyways, I know we're at 11:27 in time. Did anyone else have other questions? I know you only set up an hour for this. I thought it was an hour and a half. So
yeah, I should have set up an hour and a half. I knew I had a lot I wanted to say. I like towards like the latter half of this week, I was like, yeah, I'm probably not going to be able to fit this into an hour. I'm going to try, but I should have put an hour and a half minimum. So
Do you think
any other questions?
Do you think they're going to keep releasing models, or what do you think they're going to do next?
Oh, you mean R1 for like DeepSeek?
The quant
Like
firm. The quant
Oh
firm.
yeah. Oh yeah, they're totally going to keep releasing models. They have been up to this point. Like literally that one of those last charts I showed you all was literally them catching up by releasing other models relative to the best frontier models. Like that whole DeepSeek is not the only strong AI lab, right? Like in China. Like yeah, they've been releasing models for a while now. They literally, in order to get to V3, they had to release like V1 and different variations on V2. So yeah, they're going to keep releasing models because the thing is, like, their money for releasing models doesn't come from you using the model. They're again, Highflyer is a hedge fund. Their bread and butter is coming from like making trades on the international market, and particularly probably the Chinese stock market. So they're not really making money on any of this, but they don't need to. Like they probably made more money off of DeepSeek by shorting the market prior to America going down because after they had released the model than they would have ever made off of just releasing DeepSeek in a paid capacity as a service. Because ultimately despite only spending 5.6 million for V3, this is still a very intensive process to train these models and develop them and to improve them. So they're still probably going to release more models, and they're probably not going to be too worried about the money related to it because this is more of a side gig, side hustle kind of thing for them anyways. Like, we're not expecting to make money. We're just kind of doing this for fun, and we're going to release the models open source because we've got a hedge fund we really need to run. That's more of our main thing. And we'd rather like spend most of our time on that while occasionally taking the spare compute we're not using for that and applying it to AI because it's kind of cool.
Do you think
that's
they
the impression
released it? Do you think they released it more to spread word? Like, what are the reasons for releasing it if they're a quant firm and it doesn't even relate to them?
But again, it's just for them. First off, I don't think this is their best model. I just think this is the model they were most comfortable with releasing, right? Most people don't release their best model. They just release the one that they feel comfortable with releasing at that given time because they have something better in the backlog. So that's the first thing. The second thing is for them, I get the impression that the guy running the quant firm, the Highflyer, I think is Li Wenfeng. I think that's his name. I get the impression that he's very much like wants to improve the technology quicker. Like, I think he's more of maybe EAC is a little too strong of a word for his position on the topic, but I get the impression that he really wants this technology to get better. And again, it's more of a personal like project for fun for these quants. So they're not really super like, yeah, we're going to release a model. Why not? We don't, like we already trained it up anyways. We got another model in the works. So I think it's not a real, it's probably not entirely benevolent. I do think there's an inherent self-interest in them doing it, but I think that self-interest can potentially benefit humanity depending on what we all take away from it. Because again, one of the things that these quant firms are really good at is optimization. And they're like, because that's literally their job. They optimize complex mathematical models. So again, they didn't spend that much money on it. It's not really a huge thing. The compute was going to go to waste anyways because they weren't using those H100s on any of their like quant models. So yeah, might as well, make a model, have some fun with it, maybe release it. And again, like I said, I wouldn't be surprised if they shorted the American market because they were kind of expecting a bad reaction. That's not outside the realm of a possibility for like a hedge fund to do, to be honest. because they again, they dig into very esoteric topics of how that could potentially impact things like market psychology. So that's really more of a hedge fund thing, more than anything else. So I wouldn't be surprised if there was that sort of like self-interest as well. But yeah, there's probably some inherent self-interest, but also a desire to advance the field. Yes, Aaron.
I just added one last link for folks. So the class I mentioned is with Professor Don Song, whose work people are known. She's known for decentralized finance. So she's in the Department of Computer Science. So people that are a part of this, I did their last class last year. So they had like a good amount. I forget. It was like thousands of people in this class. It's another MOOC, but yeah, this one is actually more focused on advanced reasoning and research. So people either want to publish papers or I'm on the application side of things. So definitely take a look at that. There's a bunch of good talks on YouTube and the papers and the syllabus. So I just pasted that in the chat for anyone that's interested. Obviously, it's I don't think they have OpenAI this quarter, but last year's class there was a researcher from OpenAI. Otherwise, it's the typical usual suspects, so like DeepMind, Fair, and then a bunch of other open source researchers as well as companies. So this year's Salesforce, and then last year was ServiceNow. So there's a bunch of like interesting enterprise applications that people are looking at and applying, reasoning to the field. So yeah, definitely check that out.
Absolutely. And thank you for sharing that as well, Aaron. Much appreciated. And thank you all for sticking around this long. I'm sorry that next time, if I feel like it's going to take longer than an hour, I will make sure I allocate at least like an hour and a half, just so we're not rushing towards the end. I have to skim through so much of the paper. But thank you all for attending. I really appreciate you all taking the time here this Saturday. And I hope you all have a wonderful rest of your weekend.
All right. Thank you.
Oh, your mic works, Philip.
Oh,
nice.
Your mic works, Philip.
All right, got something.
Oh, thanks. Bye. Take care, everybody. Yeah. Yep, forgot to turn off. Hold on. Let me just turn off the recording. Sorry, everybody. It's okay. Recording ends now. Take care, everybody.